Hello friends, today we'll discuss the next topic in the high voltage engineering, that is the mechanism of breakdown in the solids, and the next type of the breakdown, that is the intrinsic breakdown. If the dielectric material is pure and homogeneous, the temperature and environmental conditions are suitably controlled, and if the voltage is applied for a very short time of period, that is the order of 10 to the power minus 8 seconds, the dielectric strength of the specimen increases rapidly to an upper limit known as the intrinsic dielectric strength. The intrinsic dielectric strength therefore depends mainly upon the structural design of the material itself, and it is affected by ambient temperature, as a structure itself might change slightly by temperature condition. In order to obtain the intrinsic dielectric strength of a material, the sample are so prepared that there is a high stress at the center of the specimen and much low stress at the corner of the uh, specimen, as shown in the figure, this figure. Yeah, we can easily say that from the diagram, the stress at the center of the solid dielectric strength of the dielectric should be very high at the center and comparatively small at the corners. Yes, while designing to the solid dielectric, the stress should be kept very high at the center and low at the both corners. The stress required are order of 1 million volt per centimeter. The intrinsic strength is generally assumed to have been reached when the electrons in the valence band gain sufficient energy from the electric field to cross the forbidden energy band to the conduction band. This is a most important condition which material should follow in order to have a intrinsic solid dielectric breakdown. In a pure and homogeneous material, the valence and conduction bands are separated by a large energy gap at room temperature. Means normally we cannot have breakdown. No electron can jump from the valence band to the conduction band without providing significant amount of energy to the valence band electrons. The conductivity of pure dielectrics at room temperature is therefore zero. Uh, there is a no conduction in the pure dielectrics, that is have a solid nature. However, in practice, no insulating material is pure and therefore has some impurities and or has some imperfections in its structural designs. The impurity atoms may act as a trap for free electrons in the energy levels that lie just below the conduction band is small. Hence, due to these impurities, always have some free electrons in the conduction band. As an electric field is applied, the electron gain energy, and due to the collision between them, the energy is shared by all the electrons. The temperature of electrons will increase. We will increase, exceed the lattice temperature, and this will result in increase in the number of trapped electrons reaching to the conduction band and finally leading to complete breakdown. By this process, there will be complete breakdown in the solid dielectrics. In electron entering in the conduction band of dielectric at the cathode will move towards the anode under the effect of electric field. During its movement, it gains energy, and on collision, it loses a part of energy. If the mean free path is long, the energy gained due to the motion is more than the lost during collision. It is very important uh, thing that the energy gained due to the motion is more than the lost during the collision. The process continues and finally may lead to the formation of an electron avalanche, similar to the gases as we have seen for the breakdown in the gases dielectrics, and will lead finally to a breakdown if the avalanche exceed a certain critical size. Hence, we can see the similar kind of avalanche as we have seen in the gaseous dielectric. Uh, the next things will be discussed in the next lecture. Thank you.